Hello and welcome back to this course for psychologists and social scientists on causal inference, directly acyclic graphs and machine learning. Welcome to week 8. This is how we get statistical inference when we're using machine learning techniques. We're going to also talk about the targeted learning approach to doing so. So before I get started, I just want to remotivate and contextualize what we're doing with respect to linear models and machine learning. So there are lots of nice reasons to use a linear model, generalized linear models as a class of models. They're very quick to fit. There's much less concern about overfitting. Even if we use the whole data set without this train test split, we're going to get the best estimate for that, the slope of that line, for instance. Might need to be more careful when we start including non-linearities. Reviewers like it. This is not a reason to use a linear model really, but it's something to be aware of in terms of how you describe and introduce techniques. I think there's much less introduction required for linear models because reviewers are very familiar with those in general. We also get parameter estimation for free. So when we fit our linear model, even though we're maybe using a predictive objective like the ordinary least squares objective as part of the sort of the linear algebra that relates these quantities to each other, you also get a set of beta coefficients for free, as it were. You don't need to then do another step, say with plug-in estimation to estimate those values. They're just given to you as part of that fitting process. And hopefully if our model is correctly specified in terms of its structure, its causal structure and its functional form, then we'll also get nice causal parameters. We also get statistical inference for free. So we get a whole load of standard errors with which we can derive confidence intervals, p-values and so on. So that's super convenient. There are, of course, reasons not to use a linear model, which we've already talked about. It's likely to be functionally misspecified if we admit that there's a lot of nonlinearity in the real world and we haven't quite identified the correct functional form a priori. For instance, if we think it might be quadratic, but actually that's just one particular possibility in the space of all possible nonlinear functions, then we might get that wrong. So it's very difficult to know if we've really correctly specified the model in terms of its functional form. And we don't therefore give the data a chance to speak, to use Van der Laan and Rose's words. We also can't handle high dimensionality. So if we've got lots of variables, tens of variables, hundreds of variables, we're going to really struggle to get convergence with our ordinary least squares objectives and a linear model. And we may also have problems with multicollinearity, whereby multiple variables are highly correlated with each other, which suggests that maybe these two variables are measuring essentially the same thing. And you end up with an ill-posed linear algebra problem, essentially, where it's hard to assign the importance to each of those beta coefficients when it's not clear where the information came from, either one or the other or both. So there are some reasons not to use linear models. In terms of using machine learning, in contrast, particularly from the point of view of parameter estimation, one of the good things is that we don't have very strong assumptions about the functional form. This was, one of the problems with the linear models. We can therefore let the data speak, and we've got lots of options available to us for this. Support vector machines, random forests, gradient boosting machines, neural networks, and so on. You can also include in there linear models as well. There are reasons not to use machine learning. As well, risk of overfitting. We spent quite some time talking about different methods for avoiding overfitting: train test split, train validation split, cross validation, nested cross validation, k-fold cross validation, leave one out cross validation. We have a lot to think about there to avoid overfitting, or at least to understand whether our model seems to be overfitting and if there's anything we can do about it. It can also take time to fit everything, particularly with big data sets and ensembles. We've got data sets with lots of variables, lots of rows. We're using ensembles with lots of complicated techniques that take time to fit, and then maybe we're using leave one out cross validation, in which case we need to train n models as well for each of those folds. We also don't get any free parameters, so all we get is this complicated machine learning black box out at the end of it, and we don't get our parameters coming out as part of the process. So we have to then do, say for instance, plug-in estimation to get estimates of those parameters. We also don't get free statistical inference. There are some exceptions to these. You can design machine learning models that parameterize a distribution, for instance. But in general, we're not going to get free statistical inference or free parameters. And so we need some way to do so. We have a solution for this free parameters issue with plug-in estimation, but we may need to consider bootstrapping or semi-parametric approaches for the statistical inference part. And indeed, today we're going to be talking about semi-parametric approaches to deriving confidence intervals, p-values, and so on from machine learning models. So in summary, there's actually only one, as far as I can see, one main reason to not use a linear model, and that is because it's likely to be functionally misspecified. Depending on your application, the other main disadvantage might be that they can't handle lots of dimensionality, high dimensionality and multicollinearity. But if you're dealing with, the regular sort of smallish data sets without this issue, then you can work around it. So really the main thing is this functional misspecification. Of course, these other things are kind of related, but maybe the real sort of stumbling point is this functional problem. So how do we deal with this? Well, we use machine learning, but then we have these two other main disadvantages that we're faced with. So arguably, you end up with more problems than you started with when you move to machine learning. In particular, you don't have any of these free parameters coming out. So you have this extra step. Well, I've already talked about that. It's not a big deal. We can handle it. The main problem that rests then is that there's no free statistical inference. So we don't have confidence intervals. So that's what I'm going to be talking about today. And we're going to be talking about the targeted learning approach. So the targeted learning approach, sometimes also known as the use of influence functions or semi-parametrics, influence curves. There are variations of which targeted learning is one. And it allows us to use powerful machine learning algorithms, say with ensembles, alongside the plug-in estimation approach to get point estimates of the treatment effect or the estimate that you care about. But the additional benefit is that you can also reduce some residual bias. So you don't only get your statistical inference out of it, you get your plug-in estimation with this approach, but you also actually improve your estimate using a targeting step. And I'll talk more about that later. One of the main limitations of this is limited to categorical treatment, as far as I can tell for now. And so as such, if you need it for other things, but also more generally, you should also consider the bootstrapping approach, which is a very popular approach to deriving statistical inference. So bootstrapping, as we'll talk about an example that's very similar to bootstrapping, but there's a lot of coverage for bootstrapping already. So the reason why I'm not talking about bootstrapping is because, if you search bootstrapping with machine learning, you'll probably find lots of resources on how to do that, whereas comparatively there's less information for how to do this sort of targeted learning approach. There are still some great references, but maybe not as many. So I wanted to take the opportunity to give a different perspective on that. And to do that, I want to just rewind a little bit to talk about what statistical inference is in general, so we're all on the same page. Let's consider what we're interested in is estimating the height of the average human, whatever reason that you're interested in that for, I'm not sure, but let's say that you are interested in the average human height. We might look at this. We might express our estimate as the expected value of y, where y is the height measured in, say, meters or centimeters. And what we're going to argue is that there are a whole lot of people on this planet, and if we were able to collect everyone, we would have access to the population value. But what instead we're going to have to live with is just taking smaller samples. So let's say I take a sample from this world. I have 500 people and I estimate their height. And I estimate their height using the empirical approximation for the expected value of y, which here is just this 1/n, where n is equal to 500 for this particular sample, multiplied by the sum of all of the heights of the individuals in this sample. And that's going to give me an approximation, finite sample approximation to the expected value of the height. And I'm going to call that mu hat 1. It's got hat notation. This is what I'm using to denote the fact that it's an estimate. It's a Greek letter because it's supposed to be sort of, something, an estimate, something that we care about. And we've got 1 because it's coming from the first sample of 500 that we've taken. But what we can do is then take another sample and so on until we have, say, k samples. That is k lots of samples where each sample may comprise, say, 500 people here, 200, 100, 550, and so on. So they don't have to be equal. But the idea is that if we were to do this repeatedly, we end up with a lot of estimates for mu. And each of those estimates, mu2, mu3, up through mu k, gives us different estimates for the estimate here. And what we'd expect is that each of these mu's would be somewhat different. It would be different because we've got different numbers of people, but also because we've got different people. This is really this finite sample variation. And so we don't only end up with a standard deviation across height. There will be a standard deviation across height in the real world. That would be another estimate we might want to estimate. But we've also got a standard deviation across these different estimates. So it's not just, there's two levels. The first standard deviation associated with height. The second is the standard deviation associated with the empirical estimates for the average height. And that can be computed if we have lots of different mu's. Now, according to central limit theorem, what's also true is that each of these different estimates for the estimand will be normally distributed. And so in other words, if we were to take all of these mu hats and look at their distribution, we'd see that there was a normal distribution centered on mu, the true value of the height. This is maybe a simplification. It's sort of a little bit theoretical, because in practice, you can't get negative height. Maybe the tails are sort of chopped off because there are very, very few people above a certain height or below a certain height and so on. But regardless, this is the sort of process, the reasoning that we use to derive statistical quantities. And what it means is that we only need actually one sample. We only need mu hat 1 here to get an estimate for standard deviation across multiple samples, because if we assume it comes from a standard normal distribution, or rather just a Gaussian, then we can compute the standard error according to this expression here. And the standard error is the standard deviation across each of these sample estimates, each of these mu's. And so the standard deviation can be computed as sigma, which is the standard deviation of a single sample, let's say this sample here with 500 people, divided by the square root of 500, divided by the number of people in that sample. And what we can see here is that if this n grew to be infinitely large, or at least as close as matters, the standard error will be tiny, because you're converging closer and closer to the true value of mu here. But we're always, at least in this example, we're going to have finite samples that are small enough to warrant the calculation of a standard error. And with this standard error, we can derive p-values, confidence intervals, and so on, because it tells us essentially how much this distribution varies around the true value here. Now, this process that I've gone through here of estimating and getting an approximation for the estimate here using this expression, it's really just the case of passing in some data to a function, and that function giving us an estimate for the estimand. And so here, y is some data, we pass it to f, some function, and it gives us mu hat here. And what we're saying is that if we assume mu varies in this Gaussian way, according to this central limit theorem, we can directly undertake statistical inference using only one sample and one estimate for mu, using this, say, equation for standard error. And in doing so, this is what a standard error tells us. As I said before, it's not the standard deviation of the height, but it's the standard deviation of the empirical estimates of the average height. And so then we can get p-values and so on around that value around the estimate that we have. So the trouble is that with machine learning, we get arbitrarily distributed estimates. The central limit theorem thing doesn't hold very well, because we're using estimators that sort of are fit to certain factors in the distribution. So we're no longer dealing with the raw data, we're dealing with models for the raw data. And those models don't behave particularly nicely. And so when we pass in different sort of samples for our data into this machine learning process, FML, not for maximum likelihood, but for machine learning, we get different estimates for tau, but these different estimates are not normally distributed. So in other words, yes, for lots of different batches of y, tau hat will not necessarily be normally distributed. And that's when we get our estimate tau. We don't get this nice closed form analytic solution for computing the standard errors with which to do null hypothesis significance testing, confidence intervals, p-values, and so on. So then the question remains, well, how do we get the same sort of benefits that we get when we're just computing the average height? How do we do that with machine learning? And so what I'm going to do is conceptualize the problem as follows. I'm going to imagine that there exists this blue point here, which is the truth. This is the estimand, the true value of our estimand for the population quantity. And when we derive an estimate, we end up over here somewhere. And the reason why I've got this sort of landscape is because I want to imagine that actually at the bottom of a mountain, that's the truth, and we want to get to the bottom of that mountain as best we can. And the further away we are from the truth, the higher up the mountain we are, and we want to be able to actually move in the right direction. And this is where you get this sort of update or targeting step associated with this process. So what I'm going to argue is that we need to take the derivative of our estimand. So our estimand in the examples that we've seen is the average treatment effect. And if we've got an analytic expression for that derivative, we're basically saying that we can work out what direction that we need to go, what the direction is of descent to take us in the right direction. So when we take the derivative of the estimand, we end up with an analytical solution, a formula essentially, and we can plug in the values that we have in our data set to compute the value of that derivative where we are now. And that's going to give us the derivative of where we are now with respect to where we want to go, essentially the estimand here, which is a bit like when you're up a mountain and you know where you want to go and you need to take a step in that direction. So you look around you, which is a bit like collecting data. And then you use those data to compute the direction of descent. So here, this gradient direction is supposed to indicate that if I'm up this side of this mountain, I can compute where I need to go by assessing where I want to go, assessing where I am with respect to where I want to go. And then I can take a step in that direction. And that's what these pink lines are used for. So the derivative actually tells us how our estimate varies in response to small perturbations. And this is a bit like finding the direction of descent on a mountain that takes us towards that true value. And this derivative is known as the influence curve or influence function. It takes a bit of derivation. This is an analytical process where you have the estimate written out, and then you need to go through a process of finding that pathwise derivative. Luckily, some very smart people have done this across a whole range of estimates for us, so we can just look it up a lot of the time, at least if we're dealing with well-used or popular estimates. And so the inference function for the average treatment effect is given here. Thankfully, it's also done for us. Now, this may also look a little bit scary, but actually, if we break it down, we see it's just full of things that we already know about. So if we start over here, for instance, we see y tilde. This is just the outcome. This is one value in your data set for the outcome that you collected as part of your data collection. And we've got here minus q t x tilde. This is actually your plug-in estimator that estimates the values of your outcome. So here you've just got the true value of your outcome minus the predicted value for that outcome. So this is just what you would compute as part of computing the mean squared error, for instance, or the absolute error. You've just got the difference between the true outcome and the outcome that you estimate. So it's kind of reassuring to know that that's here, because if you were really bad at predicting the outcome, you would expect to be a long way away. And so you'd have, you'd be high up on this hill. You've got another term here. This is Q1x minus Q0x. This is actually the conditional average treatment effect. This is before we've averaged across all the groups. We've actually just estimated the treatment effect for a particular row in our data set. We've got t equals to 1, t equals to 0 here. So this is essentially the average treatment effect for a single row, which is kind of like the conditional average treatment effect, not quite, but similar. And then we've got that quantity minus psi ATE. This is actually the treatment effect estimate, the estimate for the estimand. So it's reassuring to see these, because if we were to compute the average of this gradient, which we will do, we will take the average gradient across the whole data set. This is just for one row in our data set. What we'd expect to see is that we were both good at predicting the outcome here, so this would be very close to 0, and that actually this quantity here minus this quantity would also be close to 0, because then on average we'd be doing a good job of estimating the average treatment effect. Now, in practice, we're actually going to put in, we don't have access to the true value here, so we put in the estimate for the average treatment effect, which might seem like cheating, but actually it's then being used to compute the variance. So here is a bit like doing the individual value on a row-wise basis, like the xi minus x bar. So this gives us an opportunity to compute the variance. Then the only term that's sort of remaining that's a bit bizarre is this term out front here. And we're seeing this term G, first of all, which we haven't seen before. This is actually just another estimator. So we have Q for the outcome here. Now we have G. G is going to be used, instead of predicting the outcome, is going to be used to predict the treatment assignment. So it's also known as the propensity score model. It's the propensity to treat, the propensity of treatment. And it models how likely it is for someone to actually be in, say, the control group or the treatment group in an observational study, whether or not someone chooses to take the drug or a different type of drug. So G here is another, for instance, super learner, which is trained to predict the treatment assignment in our data set given a set of covariates. And we've got G here and 1 minus G. So in the binary case, this is just the probability of not being given treatment, 1 minus GX. And then on the top here, we've got this sort of maybe unfamiliar quantities, delta t tilde of 1. Now, this is actually just an indicator function. It just selects either this term, this fraction here, or this fraction. So delta t tilde of 1 tells us that this will give us a value of 1 when the treatment is 1. So whenever treatment is 1 in our data set, for that particular row, we'll just set this value to 1. So we just end up with 1 over gx. And then here we've got delta t tilde of 0, and this will give us a 1 whenever the treatment is 0. So when treatment is 0, this is 1 minus 1, so that's 0, and this term disappears. But in contrast, when this isn't 1, that you'll end up with this term here, minus 1 over 1 minus gx here. And so it just selects between these two. You're not actually computing a difference here. You're either using this first term or you're using this minus 1 over 1 minus gx term. And so this is sort of like the inverse propensity score. And actually, there are lots of methods in the causal inference literature that leverage the propensity score, because you can kind of either use it to say match people that had the same propensity, that's propensity score matching, or you can try and use it to sort of reweight the estimates of the average treatment effect according to the likelihood of either being in treatment or not. So on average, you can kind of compensate for the selection bias associated with, maybe more people preferring to get treatment versus not get treatment. So if you're interested in propensity score models and methods, then I certainly encourage you to look them up. But suffice it to say, for this purpose, it's reassuring to sort of see this popping up here, because because it's so common in the causal inference literature. And actually, as I'll talk about, this propensity score model helps us adjust for the fact that we're simultaneously trying to model the outcome as well as compensating for the confounding effect of treatment on of the confounders on the treatment and the confounders on the outcome. So I'll talk about that in a second. So once we've got our inference function, this expression here, we can plug some values in it according to our data, and we can use it to estimate the inference function on average, and we can use that to then take a step towards where we want to go. So again, it's like having our initial estimate, having a direction which we want to go, which is the truth, plugging in the assessment of where we are now, which is a bit like looking around us on the mountain and trying to assess what the direction is that will take us as quickly as possible to where we want to go, and then taking a step in that direction. And when we take a step in that direction, we end up with this targeted estimate. And then we also, as I mentioned before, these quantities here enable us to actually compute the variance around the estimate. So once we've got that influence function and we plug in our values, we can also use it to compute the variance. And that variance is the variance around our estimate for our estimand. We can use that to compute standard errors. This is the same equation that we saw before. This is actually the same as the standard deviation divided by the root of n, or if you square everything, if you take the square root outside, then we've got the square root of the variance divided by n. And we can use that to derive standard errors here, confidence intervals, and then also p-values. So it's almost like magic. We don't only move closer to where we want to go, but we also end up with a whole load of statistical quantities which we need for our null hypothesis significance testing. So an alternative perspective on this is that when we first do our initial estimate, we're kind of very close to being perfect already. We don't want to be too far away. At the end of the day, if we're sort of assessing our gradient, but we can't see where we want to go, we may actually not be moving in the right direction. We might be moving further away from where we want to go. And unless you've got a clear view of where you want to go, you're close enough, then it's quite difficult to take a step in the right direction. And actually the derivative is a linear thing. We get the opportunity to take one step in a straight line, and we want to make sure we're close enough for that straight line to be meaningful. We assume that our initial estimate just needs tweaking because it isn't targeted. And so when you run a linear regression with ordinary least squares, you're not just estimating the causal effect you care about. You're not just estimating the estimand. You're amortizing your accuracy across all the beta coefficients in that model, because you've got an objective that isn't targeted towards the estimand. It's a general predictive objective. You're saying, I want to minimize the predictive error of this model. And when you minimize the predictive error of a model, you're again amortizing over all the coefficients. You're not targeting your model. You haven't got an objective that directly corresponds with your objective as a researcher. And so the idea is, again, well, if our objective is kind of relevant, but it's not exactly what we want, then we just need to sort of move it back on track. So it's not targeted, but it's close. And then once we target them, the resulting estimates as a consequence of some statistical theory are normally distributed. So then we get our statistical inference out. So here's an illustration of this process. You might start with, along the y-axis is the estimand here under the true population mean, and true population distribution here, 0.0109, that's the true value. It's the perfect estimate there. And along this y value, we have different values for the estimates that we might get. So when we have our empirical estimate, our initial estimate here, we might find that the estimate is around 0.0108. And what we want to do is actually move in the direction of the true value by taking this gradient step. And that's what this step affords us. After targeting, we get closer to the perfect estimate, and we also end up with these statistical quantities that we need. So the remaining question is, how does this targeting work? There are actually lots of different ways to do this update step. The targeting process uses a submodel approach, which has certain benefits, certain advantages. But the principles are actually very basic. And I'm not going to go into the targeting method, but in general, you can actually just add the value of your influence function, your average influence function over your data set to your initial estimate. So that's what's given here. The true value, psi of calligraphic P, is supposed to represent the population, is equal to the estimate of that, psi of P hat n. And here, this doesn't just consist of the empirical distribution, but it also consists of, say, machine learning models. You might have plug-in estimators in there, plus the value of, on average, this is sort of an averaging process here, 1 over n times the sum of all of everything inside. This is your influence function. So this is essentially the gradient of your estimand evaluated at the empirical distribution that you have now, including your plug-in models. And so we're just adding the value of that gradient, the average value of that gradient, to the initial estimate. So it's a very simple update process. We've also got this OP of 1 over root n term here, which is just an error term. It tells you how fast this expression converges. And this tells you that, well, it converges at a rate of 1 over root n. And this is actually also known as the von Mises expansion. For those who care, this is a functional equivalent to the Taylor expansion. And this is just one way to do the updating step, but there are others as well. In fact, in our paper, a free lunch with influence functions paper, which is referenced at the end of this section, we go through and evaluate quite comprehensively all the different ways to perform this updating step. So I hear that probably a lot of you, at least, that don't care too much about the mechanics. This is maybe something that's interesting to statisticians, but not so much to practitioners. So I hear you ask, you don't care about the mechanics, but how do you actually use it? So the key point here is to know that when you're doing using influence functions for estimating the average treatment effect, you need 2 models. You need the outcome model, the Q, and then you also need the G method for the propensity score. This is for estimating the treatment. And then you're going to use some kind of update step. But the details of the update step and how these are used, you don't need to understand them too deeply, because there are packages in R that do this for you. And what this update step is going to do is remove that residual bias, give us our estimates, and give us our statistical inference. So I'm going to use for this example, an example taken from, I think this is Miguel Hernan's page, but I'm not entirely sure. But anyway, check out this link here and it'll have the full example. They're going to do something different to what we're going to do, but I'm going to use the same data for this, almost the same. I'm going to make some small changes here. Essentially, we've got the outcome Y and the treatment effect A. We're interested in estimating the treatment effect on the outcome. And we've got these other confounders, which form these sort of confounding paths with the outcome. So this process here, I'm going to use some binary covariates now using the R binom function. N is the number of data points. The size is the number of trials that you have in this process, this random process. So here, if we imagine a coin tossing example, we just have one flip and the probability of being heads or tails, 0.5 and 0.65. We're also going to generate some random uniform noise between 0.4 and 0 and 5, but then we're going to quantize it using the round function. Which just makes sure it's not like a big long floating point number, and then our binary treatment here is going to be another binom function where the probability is essentially expressed as this linear combination of the other confounders. This is our computation of the counterfactual outcomes, which we can use to compute the true treatment effect. Here's the observed outcome here. And then we're going to generate lots of data to compute the average, which gives us the true, a nice estimate for the true treatment effect here. Turns out the true treatment effect is 1. We're also going to do this again, but with much fewer data, or you can just sort of segment these data, take a portion out of it, so that we don't have the full 100,000 examples. In terms of the packages that we're going to use, I've installed some extra things here just to give you an example. You may need, depending on which estimators that you're using, which algorithms you're using, you may need to install some extra packages. But otherwise, what we're going to do is we're going to install the TLVerse library and also the SL3. So TLVerse is going to do all the targeted learning, the updating step, the use of the influence function, and so on. And then SL3 is another super learning package like the one we saw before, but this one has really nice integration with the TMLE3 library here, which we're going to import. So we're going to use TMLE3 and SL3. We're going to generate these data again, but only with 1,000 data points rather than 100,000, whatever it was. And then the first thing to do is to specify these models, so the Q method and the G method. And this is really concerning the superlearner process. We're kind of dealing with superlearner first, what we're going to use to estimate these key components, and then we'll consider how we do the update step afterwards. So if you want to look at what learners are available to you as part of SL3, you can use SL3 list learners, and you can select on whether the algorithms are designed for continuous or binomial problems, for example. We're going to keep things super simple, super blunt. We're just going to have two learners. One is going to be the mean, just predicting the mean of the outcome, and the other is going to be the ranger, which is the random forest. The next thing to do is specify the meta-learners. We need two meta-learners, one for the superlearner for the Q method and one for the superlearner for the G method. Remember, the meta-learners are there to combine the predictions from all of the candidate learners included in the superlearner ensembles. So for the Q method, the outcome is continuous. It's this Y hat here. It's going to be predicting. We're going to have a whole load of those predictions for each candidate learner. In this case, we've only got two learners. But it's going to be a continuous outcome. So our meta learner for the outcome is going to be a non-negative least squares learner here, which I specify. And then for the treatment, because that's binary, you can use alternatives for categorical treatments. We're just going to use this SOLNP meta learner here. We're going to specify the Q model as follows. We're going to specify the learner list. And we're going to use both of these candidate learners, the mean and the random forest here. And we're going to specify the meta learner. Same thing for the G model here, specify the learners. We're going to also use the mean and also the random forest, and then specify the meta learners, this BN meta learner we specified earlier. Then we're going to bring it all together with this learner list. A, the learner list for A, the treatment, the propensity score model is equal to G, which we specified, and then the outcome Y is going to be modeled by Q. So here are all of the steps here, just to review. Okay, and so once we've specified these, we can consider the targeted portion of this process. So the first thing we need to do is specify the nodes that are relevant to our computation. So it takes in this node list. It's going to be interpreted using this W, which is the confounders, the adjustment set, and we're going to concatenate W1, W2, W3, W4, which if you look back at the graph, there are the control variables that we need to block the backdoor pass to the outcome. We're going to specify the treatment as equal to the variable A, and then the outcome Y is equal to the variable Y. And of course, if you've got different names for your variables, just put different names in here. We're also going to specify what the estimate is. And actually, there's a function made for us called TMLE ATE, which is designed for estimating the average treatment effect, which just takes in the treatment levels that you're interested in contrasting. So when we do our plug-in estimation, when we're looking at the difference between Q under treatment and Q under no treatment, you need to tell it what those treatments are. In our case, it's super simple because we've got a binary treatment. So treatment is equal to 1, control is equal to 0. But in the categorical case, you may have treatment equal to 5, control level equal to 3, or whatever it is you want to contrast. So it's very flexible. Just got to specify these in advance. And then the final function, TMLE3, just takes in this ATE specification here, the data that you have, the node list, which you specified here, and then the learner list, which is the learner list for the superlearner, all the details of the superlearner that you defined. Print TMLE fit just allows us to review the results. So here's a review of the steps here. And then when we run this, we're going to get the estimate for the average treatment effect along with standard errors and so on. And just to review the point estimates, for the TMLE estimate, we get 1.04. Remember, the true value is 1. For the linear estimate, which is just using a linear regression with the correct control variables, we get very close to the true value, which kind of makes sense because the outcome was a linear function of the treatment and the confounders. Actually, it was nearly linear, I think. Let me just double check. There was this interaction term here. Which is, yeah. But otherwise, it's almost correctly specified with the linear model, so it actually did very well. Let me just carry on. And then the naive linear estimate, which is not using any confounders, was just Y tilde A. So this is the worst sort of model. It's both functionally potentially misspecified because it's totally linear, and it's structurally misspecified because it doesn't include the correct control variables, and this is 1.3. So this is the furthest away. And so here we see the TMLE estimate is close to the linear estimate. These aren't too far off. The linear estimate was slightly better, but remember, the superlearner that we specified was super basic. We just used the mean estimator and a random forest, but in practice, we want to include lots of learners, including linear models as well. And so actually in this case, even though the linear estimate did really well, TMLE wasn't far behind, and it wasn't a very good set of superlearners we used. And also we have to understand also there's sort of finite sample variation as well, which can affect these values. More generally, so using a different example, this is giving it on the website, the handbook for TLVerse, the library. In practice, what you might hope for is that there's a monotonic improvement. So if this dashed line is the true treatment effect here, when you use a generalized linear model, which is correctly specified structurally, you might get this point estimate with these confidence intervals. And in this case, you can see that it doesn't include the true value. We might instead use super learning and get this point estimate that's much closer to the true value, but understand that there's no confidence intervals yet because this is just an ensemble. We haven't done the influence function approach. And then when we use the targeted approach, we improve the estimate slightly because of the targeting, but we also get these confidence intervals that now overlap well with the true effect. So we see that the super learner in this case is more accurate than the GLM, and then in turn the targeted learner is also more accurate. So what you hope for is this convergence, and I would strongly encourage people to use multiple approaches when they're doing these estimates to sort of check whether there is convergence, whether you're moving in a monotonic way or whether you're sort of just scattered in terms of your estimates, to get an idea of the confidence and the convergence of your results towards maybe that there's a true value, latent value in there somewhere. So in summary, targeted learning with super learning gives the best of all worlds, at least in theory. Now in our paper, Free Lunch with Influence Functions, we actually do a comprehensive evaluation of all of these different update steps, all the different methods with super learners and so on. And we do find that actually in practice, there's a lot of variation there. So they're not always consistent. Powerful ensembles, otherwise, and targeted approaches should give you the best results, but in practice, it's quite dependent on the specifics of the data sets and the estimators that you use. As far as I'm aware, this targeted approach only works with categorical treatments, so do consider alternative methods like bootstrapping, which is well discussed, and you can find some good references for that. So here are the references for getting introductions to influence functions. There are also some blog posts online, particularly that one by Miguel Hernan, I think, but I've linked to it in that previous slide with the graph on for the simulation data. But otherwise, Fisher and Kennedy provide a nice visual demonstration. In fact, the graph that I showed before with the P tilde and then moving towards the true value comes from that paper, I believe. Hines also has a nice walkthrough of all of the steps for deriving influence functions and a discussion. And then our paper, as I mentioned, discusses influence functions, but also provides a comprehensive evaluation of lots of different techniques. So that's it for this session. Thanks for joining, and I'll see you in the next session.